Hello, welcome to the course Electronic Systems Design. Last few lectures we discussed some electrical theorems and techniques how to solve a circuit, an electrical circuit where we have multiple types of components, for example resistor, inductors, capacitors and active devices. So, those are all theoretical analysis what we do on the circuit to achieve on some output which is in terms of node voltage or branch currents. So, this is what we achieve by applying those techniques such as KVL and KCL, Kirchhoff voltage law and Kirchhoff current law, and we do some sort of mesh analysis on the circuit to get the desired output, which is the output voltage at the certain component or the load resistor. So, those are the techniques which need to be solved to get the desired output. However, when the count of those components increases, then we need to use some software or we need to take the help from computer to get the desired output. We can solve the electrical circuit for maybe for 5, 6, 10, 20 elements, 10, 20 resistors, capacitor, inductors. But if the number of component increases drastically, such as in VLSI design, we are solving hundreds or even thousands of components in a single circuit, that time it's not practical to solve it by hand on pen and paper. So, we need to take help from the computer, which is some softwares are available which solves the circuit and give us the desired output in terms of voltage and current. So, one such software which is very famous and widely used is called SPICE. This is a short form of simulation program with integrated circuit emphasis. So, this is the software which we use to solve those electrical circuits. It is primarily developed for solving the electrical circuits only. So, this software was developed earlier as a SPICE, but there are various versions of the SPICE available in the world. One very popular version of SPICE is called LTspice. LT is the initials of the company which developed this software, linear technology it was developed. So, LT stands for linear technology and then SPICE. So, this LTspice is the software generally most of the students and professionals used for solving the circuit. Very good advantage of LTspice is it's freely available on the internet, which we can download from the Google. You just type on LTspice download and the link will come. You can download it, install it in your laptop and you can start solving your circuit. So, we have circuit simulations using SPICE. So, the full form of SPICE is simulation program with integrated circuit emphasis. So, we have this SPICE. So, these are the short form of this simulation program with integrated circuit emphasis. So, SPICE is the software which is widely used for solving the electrical circuits. And as we said, there are so many versions of SPICE available, and one of the widely used version of SPICE is LTspice, which is a freeware you can download freely from internet. So a freeware SPICE circuit simulation is LTspice. So this is the software which is very much used, and this is developed at Linear Technologies. So this is the company which primarily used this version of SPICE and developed it for their internal use, and then they released it as a freeware. So this is written actually to support circuit designers. It includes an extensive library of linear technology devices. So we have this SPICE software which is used for circuit simulation, and freeware or the free version of this SPICE which is very much used is LTspice, developed by Linear Technology. This is the company which started using SPICE for their internal consumption, and then they released it as a freeware. So this was primarily written for supporting their own circuit designer which was there in that particular company. So it's intuitive that this LTspice has models which are primarily for the linear technology devices. So this linear technology company, it used to develop many integrated circuits. So there are so many models available primarily for the linear technology, which are the components developed by linear technology. However, there is a provision that you can import other ICs or other components from other companies as well. So they have a extensive library of linear technology, and if you need some other ICs which are not developed by linear technology, you can always import the model of that component from the third party. So this is always desirable to have multiple type of components, because to perform a certain function you need to have so many components from linear technology as well as from other companies. These models are generally available from the manufacturer. So, whoever is manufacturing that component, they provide the SPICE model as well on their website. You can download that model, put it in the LTspice, and LTspice can solve that model as well, just like its own native library of linear technologies. So, this is how we simulate the circuits if we have a large number of components in the circuit. So, instead of solving on pen and paper, we use this SPICE software. Now, the next thing is how do we simulate using this software, so that we are going to discuss today. So, the first thing we should know is something called schematic capture versus the netlist. So, first thing is the schematic. Schematic is nothing but the pictorial representation of our electrical circuit. So, let us take one example of a simple electrical circuit and how do we make the schematic. So, for example, we have 3-4 components. We have, let us say, one voltage source, resistor, capacitor, and we have one ground. And these are the components which are connected through wire. So, this is how, let us say, this circuit is connected. We have this voltage source which is V1, and the value of this is, let us say, 1 volt. This is resistor R1 and value is, let us say, 1 kilo ohm. This is resistance R2, value is 2 kilo ohm. Let us say this resistance is R3, which is 3 kilo ohm, and this is a capacitor, let us say C1, its value is 1 microfarad. So, this is a simple electrical circuit which we just made. It has 3 resistors, one capacitor and one voltage source. Now, from our earlier discussion, we have KVL, KCL and we have mesh analysis. We can perform that mesh analysis on this circuit and find out the node voltage and current. Let us say we have 2 nodes here, one is this node A, this is node B. So, we can perform mesh analysis on paper. We can write KVL and KCL, solve the equation and get the node voltage at A and B or any branch current in R1, R2 and R3. So, this is the pictorial way of representing a circuit. This is called the schematic or the schematic capture. However, if we want to solve this circuit using a computer, it is very difficult for a computer to read this kind of circuit. So, instead of a pictorial view, we need to create something called netlist, which is the textual representation of this circuit. So, the same circuit we can represent in terms of text, and for a computer or for an algorithm which is this CAD software which is SPICE, for SPICE it is easy to read that text, this kind of a programming language sort of thing. So, it is easy for a SPICE to solve the circuit from textual format rather than this schematic capture. So, when we make this schematic capture, we convert this graphical representation of the circuit into a textual format which is called the netlist. So, the same circuit, if we want to write in terms of text, it can be written like this. So, we have, this is called the schematic, and if we want to convert it into a text format, this is called the netlist, which look like this. So, for example, we have so many component here. So, this voltage V1 is connected between node A and the ground, which is always considered 0, and the value of this voltage source is 1 volt. So, how do we write this in the text format? This is V1, which is the name of voltage source. This is connected between node A and node 0, and the value of this voltage source is 1 volt, which is intuitive. So, this is the textual representation of this circuit. The next element is R1. This R1 is connected between again node A and node 0, and the value of this R1 is, we have kept 1 kilo ohm. So, we write 1 and K. It means the R1 resistance is connected between A and 0, value is 1 kilo ohm. Similarly, we write R2, which is connected now between node B and 0. So, we write B and 0, the value is 2K. Similarly, resistance R3 is connected between node B and A. So, between node B and A, the value is connected 3K. So, R1, R2, R3, and the rest is the capacitor, which is, the name of capacitor is C1. It is connected between two terminals B and 0, and the value is 1 microfarad. So, we write 1 micro, and farad is intuitive. SPICE knows that this is a capacitor, so the value is in farad. So, this is the textual representation of our circuit, which is given on the left, which have so many components connected together, making some nodes and branches. The same circuit, if we want to represent in terms of text, we can write like this, and there is SPICE software available which can do internally. We need not to write it by hand. It is easy for us to make circuit in graphical format, just like we connected resistance and capacitance, and there is a way of converting this graph into this text format, which is called the netlist. You see this, all the individual components have their particular syntax, which we are going to discuss. For example, the voltage source, which is connected between A and 0, and the value is 1 volt. So, this is called the netlist. So, this is the text representation of the circuit. Now, let us discuss how do we do it on the LTspice software. So, let us switch to the LTspice window. So, this is LTspice software, which when you open it first time, it appears like this. So, now we need to make this circuit in LTspice. So we go to first the new schematic. So we go to file and click on the new schematic. So this is the schematic which is opened. Now first we take the ground connection. This comes as ground. We click on the ground and place it anywhere we want, and then escape. We can drop the selected pin. Then we use a voltage source which is given here, which is voltage source. You click on here and place it here and then escape. Then you right click on it and this dialog box will open where you can specify the value, which is 1 volt for us for time being. So this is 1 volt. Then we take the resistances. This is resistance R1 which we put here. This is resistance R2 and this resistance R3 which we need to rotate. So we do Control R to rotate it and then escape, and then we take the capacitor component from the top and place it over here, then escape. So now we have all the component placed here. Now we need to fix the value of this. So again we go to R1 and do right click. It opens up this dialog box where you can specify the value, which is 1 kilo ohm. So you write 1 kilo ohm. Okay, this appears here. Similarly, R2 is 2 kilo ohm. And similarly R3, you right click and put the value 3 kilo ohm. For the capacitor, if you right click, there are so many values, but for time being we are just sticking to the capacitance value, which is 1 microfarad. U is the acronym for micro, so we put micro here. Now these are the components placed here. Now we need to connect it through wire. So there is a symbol wire here. You click it and then you can connect all these components by going from one pin to the other pin. So this is the actual circuit which we have made in the SPICE software now. This was shown in the last slide. So now our schematic is ready here. We have R1, R2, R3 connected together and voltage source and capacitor, and here is the ground. Now as I said, we need not to write the text format of circuit. We can directly generate that from SPICE. That we can do by going to view. So there is a view section here. You go to view and then SPICE netlist. If you press this SPICE netlist option, you see this is the textual format of what we have just made. This is what we have written in last slide by hand. This is V1, this is the node 1. So if you don't specify the node value, the SPICE is going to do it for you. So by random, the SPICE has assigned the value node name as N001. However, you can always write the name of wire, which is, you go to wire and right click, then there is a label net. You can write it as A, put it here, and then right click here, name it as B and put it here. Now if you see the SPICE netlist, this will be very much like our handwritten SPICE netlist. we have voltage source V1 connected between A and 0, the value is 1. R1 is between node A and 0, which is 1K. So, this is exactly what we have written by hand in the last slide. So, this is how you make the electrical circuit in the SPICE and generate the netlist. So, now few points here to note is these syntax are very much standard. If you see this SPICE netlist, all the voltage sources which you have in your schematic, these all start with V. So, V is the syntax for the voltage source. The first letter of your voltage source should be V. You cannot change it to any arbitrary value. If you are generated by SPICE, then SPICE is doing it for you. So, all voltage sources start with the letter V, and there is a particular syntax for these voltage source. This is the name of the voltage source, whatever you have given here, V1, and next two letters, these are the node numbers where this voltage source is connected. One is the plus terminal and the second letter is the minus terminal. So, these are two terminals of voltage source, and the fourth parameter is the magnitude of this voltage source. So, here we have 1 volt of voltage source. So, here it is 1. So, this is a standard syntax which is standard for the SPICE simulators. Similarly, all the resistances, you have even thousands of resistance. So, first letter of all the elements will be R, and next you can append any number R1, R2, R5 or R6 or anything to differentiate between R1 and R2, but the first letter of this should be R, so that SPICE knows that this is a resistance. Next two numbers again are node numbers where this resistance is connected. So, these are two terminals, terminal A and terminal B, and the fourth parameter is the value of this resistance. So, these are the standard syntax of SPICE simulation. Similarly for the C1, which is the capacitor. So, for capacitor, all the lines start with C, the first letter is C, and then two node, and then the value of this capacitor. And at the end of the SPICE simulation, there is a syntax which is dot end. It tells SPICE that the circuit ends here. If we want to write the comment in a SPICE netlist which you do not want the SPICE to simulate or to consider, this is just for the understanding of human beings. So, you can write the comment starting by star, and you can write anything whatever you want for your understanding. For example, this is a resistor capacitor circuit. So, you can write it any text here, and SPICE is not going to consider this. So, these are some standard syntax of SPICE which you need to know how to solve. So, coming back to the discussion, we just saw that how do we make a pictorial representation of a circuit in SPICE and LTspice and convert it into the textual form, which is netlist. So, this netlist is going to be simulated using SPICE software. SPICE is going to solve all the matrices whatever is needed to arrive at the nodal voltages and branch currents. So, when SPICE does this simulation, there are particular steps which SPICE going to perform. So, the very first stage which we need to know is the DC operating point analysis. So, the last slide we saw a circuit where we have a static voltage source which is 1 volt. It is providing 1 volt across its terminal, and accordingly some current is flowing in the branches and the node voltages are developing. Those are fixed values. So, because we do not have any sinusoid voltage source or any other thing, we have a static voltage source which is not going to change with time. So, the node voltage and branch currents, they are a fixed number. So, that those fixed numbers, they are not going to change with time, even if we kind of look at the solution in the time domain, there are static numbers. This is called the DC operating point, or simply the operating point simulation. So, how does a SPICE perform DC operating point simulation, that we need to know. So, for a DC simulation, first we need to know there are circuit elements which behave differently at DC and behave differently in the transient simulation. For example, our capacitor. Our capacitor, we all know that the capacitor for DC is a open circuit. There is no current flowing for a DC voltage. If we apply a DC voltage across the capacitor, there is no current flowing in the capacitor. Similarly, the inductor which we have, this is a short circuit for a DC operating point. So, when we are going to perform a DC operating point analysis, all the capacitors in our circuit are going to be open circuited and all the inductors in our circuit are going to be short circuited. So, SPICE does that in the simulation when it solve those matrices. For dot OP or the operating point analysis, capacitor will be assumed as open circuit or by its internal impedance, whatever it is. Complete open circuit is for the ideal capacitor. However, for the practical capacitors, we have certain series resistance which is very high, but it is finite. So, we need, instead of complete open circuit, that will be replaced by that very high resistance. So, this is how SPICE simulate the operating point analysis, or the operating point it finds out on the circuit. So, we have DC operating point of SPICE simulation. So, usually a DC solution of the circuit given that each component has its own current and voltage characteristic. So, for a capacitor, for example, we have a capacitor in our circuit. This is positive terminal, this is negative terminal, and there is a current flowing IC, which is a function of T. This flows here, and there is a voltage buildup VC across T. So, we can write the impedance of this capacitor 1 over j omega c, or sometimes we write it in the Laplace domain, we write it as c. So here we see this omega, this is the frequency of operation. So if we have very high frequency of operation, then this ZC value is very small because the denominator is very high. So the impedance is very small, it means the capacitor will act as a short circuit. However, if this omega or the frequency of signal is very small, very close to 0 or 0 in DC case, then 1 over this 0 will give you a very high number. It means the impedance of this capacitor is very high at DC operating point. So when we perform the DC simulation, SPICE is going to replace this capacitor with an open circuit. Similar cases with the inductor. We have, let's say, inductor. The current through this is IL and the voltage developed is VL. So we can write impedance ZL is equal to J omega L. So for a DC, omega is 0, it means the impedance of inductor is 0. So inductor will act like a short circuit. So these are the impedances which SPICE is going to replace the actual component with this impedances. And in DC operating point, as we said, the voltage values are static, they are not going to change. So there is a output data will be displayed as a list of node voltage and loop currents at steady state. So the output data will come as a list to voltages and branch currents at steady state. So when we make these circuits in the SPICE and we generate the netlist and solve the circuit using SPICE, SPICE look first what are the components it has, for example resistors, capacitor, inductors, diode, BJTs. And for the DC operating point, the algorithm is written such a way all the components, all the capacitors will be replaced by open circuit or its internal impedance at that particular frequency, and the inductors, they will be replaced by ZL or J omega L, and for DC, which is the 0 frequency, impedance will be a short circuit. So that those two nodes where the inductor is connected, for example between node A and node B, those two nodes will be connected by a simple wire, or those two nodes will be kind of merged together, and then the SPICE is going to solve those mesh analysis to perform a KVL, KCL and all other techniques to arrive at the output. Now the output is a static values. The node voltage will come, that will be a fixed number, and all the branch current, these are all a fixed value. So all the output data will appear as a list of node voltage and node and branch currents in a text file. So this we are going to see now how do we do it in the SPICE simulator. So let's make one new schematic and we make some sort of a voltage divider. So we take first the node 0, which is ground, then we take two resistance, one is this R1, one is this R2. We take a voltage source which is here, and we also take one capacitor just to show that the impedance of capacitor at operating point or this DC condition. So these are the components which we can connect together. So let's take a wire, connect them. And now we put the value of these resistances. So for example, this capacitor, let's say we put 1 nanofarad, resistance we put 10 kilo ohm. We right click R2 and put value as 10 kilo ohm. And this voltage source, let's say we make it a pulse. So we right click on this. So first it gives only these two values, but if we click on the advanced, then it can have multiple type of values, and we go to pulse kind of waveform. So we write initial value as 0, on value as let's say 20 volt, time delay is let's say 1 millisecond, and then rise time, fall time is 1 nanosecond and 1 nanosecond, just any number. So we just want to see what happens at the starting point or the steady state condition. So this is the value of pulse we have. The capacitor value is 1 nanofarad, R1, R2 are 10 kilo ohm and 10 kilo ohm. Now we first need to define the ports where we want to measure the voltage and current. So we go to this wire and right click, we can label the net, we call it in port, and this we define as a input port, and we connect it over here. Next we go to here and right click, label the net, we call it as a output port, and we select the port type as out, and we connect it over here. So this is the schematic which we have drawn. You see, this is a voltage source here which is supplying voltage to this resistor, which is two resistors in series, and is acting like a voltage divider. So both resistance are same, 10 kilo ohm, 10 kilo ohm. So whatever is the voltage across these two nodes, the midpoint will be at the output node. So this is the schematic. Now for analyzing, we specify the initial condition of the capacitor. So that we can do by this SPICE directives. We want to direct the SPICE that take the condition, initial condition as let's say 3 volt or so. So we write a SPICE directive here, which is dot IC V out. So this says voltage at the output node, it should be taken as 3 volt. So this is the SPICE directive we are telling SPICE to consider, and the analysis we want to perform is operating point or the OP analysis. So, we go to first the simulation and configure analysis. We choose DC operating point here. We do right click, we do click here and then OK, then this OP will come. So, we put it over here. So, this is the complete circuit now, and now if we simulate it, we can see the node voltages and then we see what the output will come out. So, this is the output or the operating point values of this circuit. We hit this green button, which is simulate button, and this list of node voltages and currents comes out. So, if you see at 0.0, we have this pulse, which is the initial value is 0 volt only. So, this voltage source is nothing but the 0 voltage. So, this in point is actually 0. So, bottom node is also 0 and this top node is also 0. The only voltage in the circuit is across this capacitor, because the capacitor initial condition we have specified is 3 volt. So, this capacitor is holding a 3 volt voltage across it. So, this output node is at 3 volt at the time 0 when we are just starting the simulation, and the other two nodes, this top node in and bottom ground, both are 0. So, this 3 volt at the output is now going to discharge through these capacitors R1 and R2. So, that we are going to see here carefully. The output node at time equal to 0 is 3 volt, which is exactly equal to the initial condition. Input voltage is 0, or the voltage at the input in node is 0. The point here to note is the current I in the C1, the capacitor. The capacitor has 3 volt across it, but the current flowing through the capacitor is very small, 3 e into the power minus 21, which is very small, or you can say negligible current flowing in the capacitor. That is because SPICE is replacing this capacitor by a very high impedance, because at operating point or the DC operating point, the impedance of a capacitor is very high, 1 over j omega c. Omega is very small. So, the impedance of this capacitor is very high. So, if impedance is very high, there is no current, effectively no current is flowing in the capacitor. That is why we see a very high number here or very low number of current here, which is flowing in the capacitor. In R1 and R2, you see the same magnitude of current flowing in the opposite direction, of course, because from the output node, current will flow towards the top in R2, and in R1 it flows through the bottom. So, the amount of current is exactly same because the resistance is same, but they are in different directions. That is why we have a minus sign here. And the current in the voltage source, which is actually 0. So, whatever is the current flowing in the R2, that is actually flowing through the I1. So, we have exactly the same amount of current flowing into the I1. So, this is how we simulate a circuit using the SPICE and perform the operating point analysis. Now, we just saw that we have a circuit of resistors, inductors, capacitors, and how do we do a operating point analysis, which is nothing but the steady state value of the circuit, where we do not have any transient source which is varying with time, all the DC sources. So, how do we come up with the individual node voltages and branch currents? So, this is something called the operating point analysis or the DC operating point analysis. However, the DC is slightly different, which we are going to discuss later. Operating point is the point where we calculate all these variables, node voltages and branch currents at the steady state value or the time t equal to 0, where we are everything is settled, whatever is the initial condition we have specified, that initial condition is just applied there. At that time, what is the circuit condition, the voltages and currents. So, till now we have just seen how we can use a resistance, inductance, capacitance, all these kind of passive elements. Let us see how do we incorporate the active elements or the semiconductor devices, for example diode, transistors, how do we use them in the circuit and do the operating point analysis. So, the first thing we need to discuss is when we make these circuits using semiconductor devices, we have diodes, resistors in series and parallel. So, these semiconductor devices, they are not linear devices. So, the characteristics of these devices are exponential or some other quadratic equations, they are not linear devices. So, when we put these devices in the circuit, we first need to know what is the operating point of the circuit, then only we can solve for the transient simulations. So, first we need to find out, when we are just placed the device and applied the DC voltages, what is the drop across the device and what is the current flowing in the device. So, that analysis we need to do, and that we do with something called load line or the Q point of the circuit. So, let us discuss that, what is the load line of a circuit. So, for example, we have a circuit which is nothing but a voltage source. In series we have a resistor which is R, and then we have a diode connected like this. This voltage source is VSS, let us say this is positive, this is negative, and the voltage drop across the diode is VD. We assume that there is a current flowing in the loop is ID. So, we can write VSS is equal to R times ID plus small vd. This is the KVL we can write inside this loop, and if we make a plot between ID and VD, so the y-axis is ID, the diode current, and x-axis is the diode voltage VD. When we have the diode drop is 0, for example, we consider the diode drop is 0, there is no drop across the diode, then the current in the circuit will be simply VSS divided by R. So, there will be a point when the voltage drop between the diode is 0, it means here. At this point, we have this VD equal to 0, then the ID will be VSS divided by R. And there will be another point when all the drop is across the VDD only, the diode drop only. At that point, VD will be VSS. This is the maximum voltage drop it can have across the diode, and at that time the drain current will be, or the diode current will be 0. So, these are 2 points. If we connect these two points. This is called the load line of the circuit. So our circuit is always going to be only in this line, because this is these are the two extreme of this circuit. Now if we plot the diode characteristic on this circuit, diode characteristic we have seen is something like this. This is the diode characteristic. So this circuit need to satisfy both the condition. It has to be on the load line and it has to be on the diode characteristic as well. So the only solution which we can find here is the intersection point of these two lines. This point is the point where the circuit satisfies both the lines, and this is called the Q point. Or the quiescent point. So this is the load line and this is the diode characteristic of our diode which we are using in this circuit. Now if we apply the signal on this circuit, any voltage change we are going to apply across the diode, that change is going to disturb this Q point. So Q point will also move like this, and this is what the input and output characteristic is. This is the input voltage and this is what we get, the output current. So this is how we can use this circuit as a amplifier as well. We apply a change in the voltage and we generate the change in the current, and this Q point is now going to shake because of this applied voltage. So let's see now how it look like in the SPICE when we do the SPICE simulation of this simple circuit. We go to new schematic and then we make this simple circuit. We first take the ground, then we take a voltage source, we take one resistor, and we take one diode as well. So this is the diode symbol, we click it and we place it here. So now we need to put the values of this. So R1, let's say we put it 1 kilo ohm. Diode, let's say we take a model, a realistic diode which is developed by linear technology. So let's say we take, let's say this diode model we take, and voltage, the value of voltage source, we can even have a fixed value, but we want to calculate the complete characteristic of diode. It means we need to sweep the value from a very low value to the very high value. So we have to make it a variable. So how do you make it a variable or a parameter in SPICE? You put it in the curly braces. So we put this curly braces and then we write, let's say capital X, which we are going to sweep. Curly braces closed and then we close it. So now the value of this voltage source is X, and this X we are going to sweep from a very low value to a very high value. Now we connect these elements together using wire. So this is the complete circuit. Now we name these nodes as in and this node as out. So this is the complete circuit. Now we need to specify what we want to do. So first is we want to sweep this variable from a very low value to a very high value. So we need to direct the spice to change it. So we go to this dot t, which is the spice directive, and we write this spice directive as dot step param capital X, and now we are going to change it from 0 to 5 volt with a step of 0.1. It means the circuit need to be solved for x equal to 0, then it need to be solved for x equal to 0.1, 0.2, 0.3, 0.4 and so on up to the value of 5 volt. So these are the total steps we need to take for x. So this is the spice directive for that, and we need to now perform the operating point analysis. So we go to simulate, configure analysis, and we do DC operating point dot op. So this is the complete setup. Now we are going to solve it where x is swept from 0 to 5 with a step of 0.1. However, these are only the OP simulations which we are doing at different values of x. This is not a DC sweep. Here we have operating point analysis of the circuit, and we are sweeping x from 0 to 5 volt. So let's simulate this circuit. If we simulate it, then the output comes in this window. Let's enlarge this. So on the x axis you already see this is changing from 0 to 5. It means this is the parameter x which is changing from 0 to 5, and now we can plot any trace. So for example, we add the trace which is the node voltage at the output node is there, so we want to plot the voltage at output node. If we plot, this comes out something like this, or we can delete this trace from here and we can add any other trace. For example, we are plotting now the diode current which is ID1. So we click ID1, it appears here, and then we click it. So this comes out to be like this. So now the y axis is our ID, the diode current. However, the x axis is still that x parameter, it is not the VD or the diode voltage. So we go to this x axis, right click, and then so to plot this drain current versus the diode, to plot this graph for the y axis at diode current and x axis at drain the diode voltage, we go to x axis, do the right click, then currently the quantity plotted is x, which is the parameter. Now we need to change it with the voltage at node out. So capital V and then out. This is the voltage across the diode. So we plot this thing, then it look like the diode drop. So this is the diode characteristic of this particular 1N5817 diode. So, this is how you simulate the circuit using SPICE. So, here we see we have this simple circuit which has a voltage source, resistor and the diode, and we can calculate the diode characteristic using the dot op analysis. The one point here to note is we did not do the DC sweep. DC sweep is something different and dot op is something different. In operating point, what we are doing, we are changing the value of x by increment and calculating the steady state condition of that circuit at that point. However, in DC, this is not the thing. In DC sweep, we sweep the voltage from very low to a very high value, and then we arrive at the solution, which is very different than the operating point analysis. So, here we performed the operating point analysis using the LTspice software. So, this is all for today. Thank you.